And welcome to the Valve Selection Safety webinar. My name is Bob Sarber, and I'm a sales engineer at Swagelok Pittsburgh. I'm going to be going over the various design considerations when selecting a valve and talk a little bit about valve types and applications. Now, since this is a very broad topic for a 30-minute webinar, it's going to be more of a high-level overview than a deep dive, but hopefully we'll generate some questions and you can follow up with us afterwards. So first, we're going to go over the basic system parameters that need to be considered when selecting a valve. Those include flow, pressure, temperature, media, viscosity, and environment. So flow occurs when a fluid or gas moves to an area of high pressure to low pressure. In a valve, flow is from the higher pressure inlet to the lower pressure outlet. The flow through a valve depends on a number of factors, including the diameter and shape of the flow path. The flow coefficient, which is provided by the valve manufacturer, can be used to help select the right valve for an application. The flow coefficient is represented in valve specs as C sub V, and a higher C sub V means a higher flow rate. Keep in mind that higher C sub V does not necessarily mean it's a better valve for your application. The C sub V is the number of US gallons per minute that will flow through a valve with a 1 psi pressure drop at 60 degrees Fahrenheit. So the flow coefficient of valve is a relative measure of its efficiency at allowing flow. For compressible fluids like gases, calculating C sub V is a little more complex, but it's still an effective way to size valves. Valve design factors that influence C sub V include the size and geometry of the flow path. For example, the larger the orifice, the greater the flow capacity. An example on this slide, both valves contain half-inch tube connections, but the ball valve on the left provides minimal resistance to flow. It has a C sub V of 7.5, while the needle valve on the right has a flow path that restricts the flow and has a C sub V of only 2.1. Swagelok publishes a valve sizing bulletin that you can find on swagelok.com, and it can help you pick the appropriate C sub V for your application. Next parameter in selecting a valve are pressure and temperature. And we put these two together because they affect each other. For pressure, you need to consider system maximum pressure, which is the maximum pressure the valve could see, and operating pressure, which is the normal operating condition. Like pressure limitations, every valve has a maximum minimum design temperature also. It shouldn't be exceeded. Temperature of your application will affect the allowable pressure. When temperature rises, the strength of materials decreases. With valves, that usually means that as the temperature rises, pressure rating goes down. The seal material is often the pressure temperature limiting component of the valve. The pressure differential is also important for flow. Delta P is the difference between the upstream and the downstream pressure across the valve. The pressure drop occurs when a fluid moves through a valve and is required to have flow. A valve with a globe pattern will have a higher pressure drop across the seat than a similar sized ball valve where the flow is straight through. With respect to valve selection, the higher the pressure differential, the more impact system pressure might have on wear of internal components. System media is another important consideration. Two primary forms of system media are gas and liquid. And media can be anything from inert gases like nitrogen or argon to corrosive media like hydrogen sulfide. When selecting a valve, you want to think about valve construction and how it relates to potential leakage. For instance, a metal-to-metal diaphragm seal may be more appropriate for corrosive gases than a soft-seated valve with a plastic or an elastomeric stem packing. Chemical compatibility is another important consideration. For example, embrittlement or stress corrosion cracking can occur if the wrong material is chosen for your media. There's a number of chemical compatibility charts available on the internet that can help you select chemically compatible components. Cole-Parmer and DuPont are two that I use often. The viscosity of your system media also affects flow coefficient. Tar picture here is highly viscous, flows very slowly, And to achieve the same flow rate as a liquid with a low viscosity, like beer, you'd have to select a valve with a much higher C sub V. The last system parameter we're going to talk about is environment. It's important to consider the physical location of your valve. Will it be in a climate-controlled environment or outside exposed to the elements? The corrosiveness of the environment will also have a major impact on the material selected for the valve. For example, will it be in a saltwater environment like on an offshore oil rig? Vibration should also be considered. Will it be close to a pump or compressor and exposed to high vibration? Now we'll talk about valve function. Valves serve 5 primary functions, which include on-off, flow control, directional flow, overpressure protection, and excess flow protection. Shown for each type are the most common industry symbols for valves, which are important when reading P&ID diagrams. The next type of valve function is flow control. The purpose of this type of valve is to regulate flow through a system, whether by simple regulation or fine metering. Needle valves are the most common type for flow control, but they can also be used for on-off control. And although plug valves are primarily used for on-off control, they can also be used to throttle flow. The third type of valve function is directional control. The purpose of this type of valve is to ensure flow in a desired direction. Although check and ball valves are different in design, both are capable of directional control in very different applications. Symbols shown here are for a check valve and for a three-way ball valve. The next type of valve function is overpressure protection. This valve is designed to prevent system pressure buildup beyond a set pressure. There's 2 types of valves in this category, relief valves and rupture discs. Relieving devices act as a last resort and are designed to operate if an overpressure situation occurs. And finally, the last valve function is excess flow protection. As the name states, this valve contains uncontrolled release of system media. The ball valves are some of the most common on-off valves you'll see. So we'll look at them first to show some of the key features of an on-off valve. Basic components of a ball valve are the valve body, the ball, which contains the orifice, which can be full port or partial port, the stem packing, which prevents leakage to atmosphere, the packing nut, which allows for packing adjustments, the handle, and the end connections. The advantages of a ball valve design for on-off service are the straight-through flow path, which offers minimum pressure drop and component wear. There's fast quarter-turn actuation. It's a low cost to automate, ease of maintenance, and the valve position is indicated by the position of the handle. There are 2 ball types used in ball valves. The Trunnion style ball valve shown on the left is good for high flow applications, as there's less friction between the ball and the seal. They require lower operating torque due to the Trunnion style ball. These are commonly found in higher pressure applications, up to 10,000 psig. The floating style ball valve is shown on the right are compact, and they seal in both high and low pressure conditions. The disadvantage of this style is that they're more susceptible to wear if abused. For example, if they're partially open to try to throttle flow, the flow is going to be directed against the seat, which can lead to premature seat wear. These are commonly found in general purpose and instrumentation applications. Ball valves can come in 1-, 2-, and 3-piece body designs. Advantages of 1-piece body design are elimination of leak points, very low dead space, bidirectional flow, they have adjustable packing, no elastomer seals. The 2-piece Trunnion style end screw design has seats that are compressed against the ball using springs. These are good for applications with high flow rates or higher pressures. They're easy to assemble, and the Trunnion style reduces the operating torque. Three-piece floating ball design advantages include compensation for wear, pressure changes, and temperature changes. It's easy to rebuild the seats. And they have a flexing seat design which maintains leak-tight upstream and downstream seats and seals in both low and high pressure applications. Another feature to look for in ball valve design is a blowout-proof stem design. As shown on the right, pressure is always acting upon the bottom of the stem, trying to push the stem up. So when the stem is assembled from inside the valve body, as pictured on the left, the stem is held in position by the stem housing. This means the stem can't be blown out by system pressure like the valve on the right. Next, we'll look at needle valves. Shown here, a typical needle valve is made up of a packing nut, which contains a stem and allows for adjustment of stem seal, the bonnet, which houses the stem and the packing, the stem, which controls flow, body, the packing, which provides a sealed atmosphere, the stem tip, which helps control flow and allows for leak-tight shutoff, the seat, which in this case is integral to the body, and finally the valve orifice. Things to consider when selecting a needle valve include the fact that they're slow opening, which enhances their ability to throttle or regulate flow. Do you require non-wetted threads? If the threads are wetted, there's potential for lubricant removal or contamination. And you want to select the right stem tip for your application. Needle valves have different bonnet types that affect performance. Bonnet is a component that contains the thread that drives the needle. There's three types of bonnets: integral, screwed, and union bonnet. The integral bonnet's the most compact with the least number of components. Bonnet's an integral part of the valve body, and the packing is typically above the threads, which means the threads are wetted. There's potential for washout or contamination of the thread lubricant. Spring-loaded packing can be adjusted with a packing nut to compensate for packing wear. And it has a rotating stem, so the stem tip is rotating at the seal point. That can lead to seal wear over time. There's a variety of stem tips depending on whether you're using a valve to regulate flow or for on-off service. In screwed body construction, the bonnet's screwed into the valve body. This style typically has non-wetted stem threads, as the packing, as shown here, is located below the threads. This is the packing. They may have non-rotating stems, which will extend seal life. They're slightly larger in size than integral bonnet valves because they have more components. The packing adjustments are possible, but a little more difficult than with the integral bonnet valve. In union bonnet construction, the bonnet's connected to the body with a bonnet nut. This design eliminates the potential for accidental disassembly when making packing adjustments. It also prevents seat damage when making packing adjustments. And this style is good for higher pressure applications. Needle valves may be available at different stem geometries, which can include ball, V, or plastic tips that will allow for shutoff service. Ball stems are good for shutoff. Metal-to-metal seal provides good chemical resistance and are good for high temperature applications. And the ball has a machined flat on the top to provide a consistent sealing surface. Regulating stem has more of a V shape, which allows for regulation of flow. But a metal regulating stem tip is not recommended for repetitive gas shutoff. A soft seat regulating stem has a soft stem tip for reliable gas shutoff. The regulating stem tip V shape allows for flow adjustment, but the soft seat material may have chemical compatibility issues depending on your media, and it's more limited for high temperature applications. Another type of flow control, which is more accurate, is fine metering. These valves are characterized by small orifice size, thin needle, more pronounced globe pattern. They may have a micrometer type handle. These valves are typically found in laboratory environments where high precision is important. It's important to note that some metering valves, such as the one shown here, are not designed for shutoff. In summary, needle valves are a proven design. They've been around for a long time. They're available for high temperature applications. They're available with metal to metal seats or with soft stem tips for gas shutoff applications. Disadvantages include a tortuous flow path, which increases pressure drop across the valve, and actuation time. It can require anywhere from 2 to 10 complete turns of the knob to completely open a given needle valve. These are commonly used to control variables such as flow, temperature, pressure, or level within a required control range. But there's also applications where a needle valve would be preferred to a ball valve or other quarter turn valves for shutoff applications. One example would be oxygen service. Since oxygen is highly flammable, you only need ignition and a fuel source to ignite it. A quarter turn ball valve should not be used. The reason being that because of the quick opening, any particulates in a line upstream of the valve will be carried downstream at a high velocity when the valve's open. When those particles strike a surface in the system, the impact energy is released as heat, and these small particles can become hot enough to ignite larger materials in the system. So needle valve, which opens slowly, reduces the downstream velocity and the risk of ignition. Now we'll look at bellows valves. So bellows valve is a type of needle valve, but a needle valve has a stem packing, which creates a sliding stem seal. Because of this sliding seal between the stem and the packing can wear over time, potentially resulting in stem leakage. For applications where you've got hazardous, toxic, corrosive, or expensive fluids, you generally can't tolerate stem leakage to the atmosphere. A bellows valve is a packless valve. There is no packing. The bellows is basically a tube with convolutions to allow it to flex, and the bellows creates what's called a static stem seal. The only way to experience stem leakage is if the bellows itself ruptures. And some types of bellows valves even offer secondary containment by adding packing above the bellows seal. This animation illustrates a packless design. There's no packing to wear as the stem moves up and down through the bonnet, and the system fluid is contained within the bellows as the valve opens. There's two basic designs for bellows valves. In the conventional design, the stem is located inside the bellows. The top of the bellows fits under the dome top of the stem and is welded to the upper stem. When the valve is open, the fluid enters the bellows. The inverted design has the bottom of the bellows welded to the stem, so when the valve is open, fluid does not enter the bellows. In general, the inverted bellows design is used for higher pressure applications, and it's easier to purge and clean. So if these aren't requirements for your application, a conventional bellows is probably a lower cost option. Bellows valves can be used for flow control and for on-off applications. They're ideal when working with hazardous, corrosive, toxic, or expensive media where stem leakage to atmosphere can't be tolerated. This slide shows some of the common industries that use bellows valves, but these are a good choice wherever you have these types of media. Now we'll look at diaphragm valves. Diaphragm valves, like bellows valves, are also packless valves. The diaphragm is located between the bonnet and the body. Like the bellows valve, will not leak to atmosphere unless the diaphragm ruptures. Some diaphragm valves also come with secondary containment. There's 5 types of diaphragm valve designs. The spring return, where spring is used, let me get back, I threw that too fast. Spring is used to maintain contact between the stem and the diaphragm. In a tied diaphragm, the stem is tied to the diaphragm to ensure it raises as the diaphragm flexes. These are good for high flow and long diaphragm cycle life applications. Springless diaphragm has no stem, and the diaphragm seals directly against the seat. A radial diaphragm is similar to the springless one, but uses a V-shaped diaphragm, which minimizes entrapment areas. And finally, the Weir style diaphragm, which is similar to the springless and the radial designs. The weir refers to the flow path. These can be mounted at different angles to drain easily for sanitary applications. Advantages of diaphragm valves are that they operate very cleanly, have very few moving parts. They have a fully swept flow path, minimizing entrapment areas. There's minimal particle generation because of few moving parts. All of these make it an ideal valve for high purity applications. There's no threads in the wetted areas, and these are available in many configurations. Now we'll look at check valves. The third type of valve function is directional control. The purpose of a check valve is to ensure flow in a desired direction. Check valve will close to prevent reverse flow. It's important that the check valve closes fast enough to prevent reverse flow, but also that it's stable when open. A spring check valve is a check valve in which the ball or the poppet opens and closes based on the force of the spring. When the forward flow of the fluid exceeds the force of the spring, the valve opens. When there's not enough flow to open the valve, or when there's reverse flow, the valve closes. The lift check valve, top left, is a check valve in which a disc, sometimes called a lift, can be lifted up off its seat by higher pressure of inlet or upstream fluid to allow flow to the outlet or downstream side. These are also referred to as springless. The swing check valve, which is not pictured, is a check valve in which a disc swings on a hinge, either onto the seat to block reverse flow or off the seat to allow forward flow. These you usually see in larger diameter applications. Check valve generally has two closure types, ball and poppet. The ball will allow some leakage and is generally used in liquid and higher pressure applications. A poppet style check valve is generally leak tight and therefore better for gas service. Some check valves can come preset from the factories. Others are designed to allow adjustment if your system requires fine tuning, for example, with an adjustable spring. Some common terms to understand for check valves: the cracking pressure, which is the pressure differential from the inlet to the outlet, in which the first indication of flow occurs. The cracking pressure range, which is the maximum to minimum upstream pressure required to open the valve. And the reseal pressure is pressure at which there is no indication of flow. Now we'll look at relief valves. Relief valves offer overpressure protection, and this valve is designed to prevent system pressure buildup beyond the preset pressure. There's two types of valves in this category: proportional relief valves and safety relief valves. They act as a last resort and are designed to operate if an overpressure situation occurs. The overpressure protection is crucial for safety. The selection considerations include set pressure, service and maintenance, the fluid viscosity, back pressure, connection size and type, and temperature. What's the difference between a proportional relief valve and a safety relief valve? A proportional relief valve opens gradually as the pressure increases. Consequently, they do not have a capacity rating at a given pressure rise. Therefore, they're not certified to ASME or any other code, and they should not be used as an ASME safety relief device. They reseal once pressure drops below the set pressure. The resealing pressure is always lower than the set pressure. A safety relief valve opens rapidly when the system pressure reaches the set pressure, and they close when the system pressure falls below the set pressure. They're similar in appearance to a proportional relief valve, but they open quicker and they have a higher relieving capacity. In summary, overpressure protection valves are designed to remain closed unless the pressure exceeds a component setting. They have to be installed in the proper orientation, and you need to understand your application so you choose the right valve for your need. The final valve function is excess flow protection, and as the name states, this valve contains uncontrolled release of system media. The spring-loaded poppet remains in the open position during normal system operation, and if an excess flow condition occurs downstream, such as due to a line break shown here, the poppet rapidly moves to the trip position. stopping uncontrolled release of process fluid. When the system pressure equalizes through the bleed vent, the spring automatically resets the poppet to the open position. So just remember, excess flow valves permit flow in either direction. They control flow in only one direction. If the flow exceeds the trip range, the valve will close. The valve reopens when the pressure is restored. It's important to remember this valve does not completely close. It will continue to allow leakage at about 1% of the trip range. This eliminates the potential for hazardous pressure buildup behind the valve. Finally, they're not intended to protect against small leaks. And that wraps up my presentation. I'll turn it back over to Gary.
All right, good job, Bob. Thanks for your time and the detailed overview of, I guess, the different valve categories, features, benefits, advantages, and when you choose to use one in your application or system. So now, thanks for everyone joining us here. We have a couple minutes, a minute or two here. If anybody wanted to chime in with any questions or comments or just general thoughts that they may have from that, by all means, like I said, we do have the recording going, so everyone will have access to that and can share it as needed or reference it down the line. But don't hesitate to unmute, say something, put something in the chat, or as time goes on, if you do have further questions or would like to see some additional information on any of this, reach out to Bob, myself, or anyone else here at the organization, Swagelok Pittsburgh, that you have contact info for, and we'll make sure we get you what you need.